Before I submit this, I want to make sure that I did correctly the last week's.
Yeah, that looks good.
Okay, I tried to kind of outline the white since it's hydrogen.
Yeah.
So can I submit it now?
Yeah. All right, so we'll do review today. Just a couple of reminders. So we'll still have lab this week to keep us on track. And that does go for the online people too, so make sure that you're doing the lab if you're online. And then if you're in person, so yes, I did include like the YouTube links on yours, but they're just kind of there for information, and we'll be doing all of that in person on Wednesday, so that should be fun, looking at those reactions. And then of course, midterm on Wednesday. There's my pen. So we'll do review today. And so your midterm, the in-person one, is kind of more free response. There's still a couple of multiple choice questions at the beginning. Oh, actually, I think I have it all free response right now, which I think is better. All right, so let's do some review questions. So the first type of question you have is classifying things. So classify the following. and you had to distinguish between an element, compound, and then a mixture, and that was homogeneous mixture versus heterogeneous. And so let's try it with the following substances. Oops. So we have C60, methane, cheese, C21, H30, O2, and a Java chip Frappuccino, which I think they took it off the menu, didn't they? All right, so take a few minutes for that. All right, let's hear what we got. So what did we put for C60? Element, excellent. So right, it's one of those allotropes, don't let it fool you, even though it's many of the same elements, so good. Methane. Compound, so good. So you are expected to kind of know, your basic small molecules, but I think we've talked about methane a lot. And ammonia would also be under there. Cheese. What do we think for cheese? So mixture, and then what kind of mixture? So homogeneous or homogeneous. And this could be one, right, that you feel the need to clarify too, because, right, homogeneous, that's kind of, if we're thinking about like cheddar cheese or just any of our usual cheeses that are big solid block. But, let's again say you got confused on the exam, just kind of write what you're thinking. And, what if you have jalapeno cheese on the brain or something, or Swiss, right? And then you could write, well, that would be heterogeneous. And I probably misspelled that. And so just, again, right, clarify in the exam if you're unsure, or, let's say you just you weren't sure what methane was, maybe you could say, hey, I think this is a compound because I think it has a formula, and at least just kind of explain your logic so I can tell what you're thinking. All right, what about this one? So C21H30O2. Compound, so good. Another defined chemical formula. And then our last one here, Java chip frappuccino. Heterogeneous mixture. Excellent. So all chunky, right, different throughout. All right, so then you'll probably have a conversion problem. And so I could give you a random conversion. And let's practice this. So now let's do convert 467,000 kilogoops to floof if there are 19.5 goops in a floof. So you may get made up units on the exam. 467,000 kilogoops. So these are just zeros. And kilogoops. And you're given 19.5 goops in a floof. So do we have kind of answers? walk me through our steps here. So what do we have to do first, especially because we were given kilogoops. So what do we do?
We need to divide the 67,000 by 1,000.
So I wouldn't divide though, right? Because we want to go from kilogoops to goops, right? And so how many, when you have kilo, what is that times your base unit?
10 to the power of 3.
Yeah, so 10 to the power of 3, right? So, or 1,000. So we're saying we have 1,000 goops, right? In 1 kilogoop. So if we want to get to goops, then we need to multiply by 1,000, right? So let's do that. Get it, right? Because again, kilo is just our prefix of our metric unit. So just set up our dimensional analysis. All right, so I won't plug it in yet, but now we're in goops. And so now the last step, okay, so now there's 19.5 goops in a floof. And so again, maybe if you need to rewrite this as your ratio first. So that kind of helps us, right? So we can see if we want floof, we need to get floof on top. And goops will cancel out on bottom. And so what do we get? Let me plug this in and fire up my calculator. So times 1,000 divided by 19.5. That's 1, 2, 3, 4, 5, 6, 7. So like 2.4 times 10 to the 7th roughly. And we should give it proper sig figs, so 3 sig figs. So rounding it to 2.39 then times 10 to the 7th floops. Questions on that one? All right, let's do another conversion practice. This time, this will be your regular units, but you shouldn't let the floops and goops confuse you. But let's just do a standard convert. We'll do 7.76 times 10 to the negative 11 megameters to picometers. Do we have answers for this one? Still working. So kind of walk me through, what are we thinking for this problem? Just kind of do two different ways to approach it. What do we know? So what's megameter? Do we remember what power that is? So 10 to the 6, so that's by our base unit. Good. And right, I would just kind of do a two-step conversion for this one. So, okay, we're thinking about going from megameters right to meters. Okay, so that's a factor of 10 to the 6. We could write out that we have 1 times 10 to the 6 meters in 1 megameter. So that gives us one conversion factor. And then what's pico then? Negative, well, what'd you say? Sorry, 12? So negative 12, so 1 times 10 to the 12 picometers are in 1 meter. Just converting it to positive units. And so now we have our two conversion factors, so this looks good. So now we can just, again, use our dimensional analysis. So now I'm just setting up what we went through. So, okay, megameters, so let's put 1 times 10 to the 6 meters on top. So megameters cancels. And then now I need to put meters on bottom so that we are left with picometers. And so now we could add up the exponents if we felt like doing some mental math. So right, negative 11 plus 12, so that's 1, then plus 6, so 7. So 7.67 times 10 to the 7th picometers. Or of course you could plug it into your calculator. And we could also see that, yes, we could have done a direct conversion factor, right, figuring out the difference between those two. So 10 to the 6 and 10 to the 12, that's 10 to the 18 difference, so that comes out as well. But again, less intuitive than our two-step method. All right, so next part will be some periodic trends. So let's just do some practice problems. So which has the largest radius? And then let's go phosphorus or chlorine. And then which has the highest ionization energy? So that's phosphorus and chlorine again. So take a few minutes, look at your periodic trends. What do you remember? right, I would have your periodic table probably annotated with the trends in a way that makes sense to you. So which one has the largest radius? What do we remember about the radius? So who has the bigger radius? Is it? What do we remember about our radius? Yeah, so it should be phosphorus. So what's the trend of the radius, right? Let me pull up. Exactly. So we go across, right? Our radius decreases. So go back, right? Remind yourself why. And we could look at it. So sorry, I was trying to pull up the periodic table. And so we could turn around or look at our periodic table. So phosphorus and chlorine, right? They're on the same row here. So just like she said, okay, the trend is as we go across, it gets smaller. And so kind of don't forget the Y, though. And we can sketch out really quickly what's going on. So remember, they're at the same distance. So we have 5 valence electrons versus chlorine's 7. And so we just have more electrons in the same orbital, right? So effectively the same radius, so that increases the effective nuclear charge. So that means chlorine, right, is going to contract smaller versus phosphorus. And then, of course, right, radius increases as we go down and add more shells. And then what do we remember about ionization energy? So who has the highest ionization energy? So chlorine, and right, kind of opposite trend from your radius. So same explanation, except this time it's really close to fulfilling the octet. So it's not going to want to pop off an electron. And you might have to remember, right, what is ionization energy? So that's just taking your energy to kick off an electron and make the M plus cation. Obviously, that's not favorable for these, right? We can see that in their oxidation state, that they want one electron. So this is unfavorable, especially as we go across and get to our noble gas configuration. All right, so there'll be some temperature conversion stuff. I don't think it'll be too difficult. There might be a different formula than you're used to. So just kind of watch the formula given. But really, if you can plug in the formula, you should be fine, because it will be different. And so let's just practice one. So convert 330 3 degrees Fahrenheit to Celsius. And again, I'll provide you the formula. So this one is just a standard formula. But like I said, on the exam, it may be different. All right, so convert that to Celsius. Just make sure you can plug and chug. And so just plugging this one in. So again, right, what's it called? PMEDAS, the parentheses, multiplication, division, right? So it's just order of operations, nothing too difficult. So of course, do your parentheses first. And then multiply it by our factor here. And so do we all get about 167? Excellent. And then 3 sig figs. All right, good. So let's try. You'll have a question just like this on your exam. And so first I'll let you kind of think about it, and then we'll go over the trick. So we have a sheet of particle board. Is cut to a length of 6 feet and a width of 3.5 feet. It weighs 60 pounds. So given the density is 53.7 pounds per foot cubed, what is the thickness of the board? Take a few minutes to think about that. What do we know? You have formulas, kind of done stuff in lab. So how do we approach this? What thoughts do we have? What information were we given?
I thought we something of density.
So then, oh, yeah, so density, mass over volume.
I expanded the formula for volume, which is length times breadth times height.
Perfect.
And then I substituted the values in the formula.
Excellent. So this looks great. So let's go through that together, though, on what she did here. And so, yeah, you could either kind of substitute it in as well right away or just kind of work through it piecemeal. So that's kind of what I did, is kind of first solve for our volume, and then we'll plug it into this formula. So volume is equal to, right, mass over density, or again, like she said, you could have gone ahead and substituted it into here, and then you can start solving. So 60 pounds divided by our density. I'm just writing it this way so you can see the dimensional analysis, right? So we get feet cubed, which is again our hint to go back to there. So then I get 1.12 feet cubed is equal to our volume, which is again length times width times height. And so then just keep going with the algebra. So we were given height and width, or excuse me, length and width. So 1.12 feet cubed is equal to 6 feet times 3.5 times h. And so what do we get for our height? And so just watch the units. So this one didn't specify what to give it in, so just make sure you write, so in this case, 0.0532 feet. And make sure giving, or 3 I should say, 3 feet, so 3 sig figs, so that's appropriate there. Questions on this one? So like I said, you'll have one pretty similar to it on your exam. Ooh. Sorry, just trying to glance at your exam. So yeah, it should be very similar. So as long as you can follow this process again, that will be good. Let's see, we're almost. Let's do a few electron configuration practice problems. So write the electron configuration for the following. So this is antimony, and that's neutral. And then let's do sulfur, but let's do sulfur 2-, so charged. And let's do tin 2+, so again also charged. So 1 neutral, 2 charged species. Again, take a few minutes for that. All right, do we have the electron configuration? Let's start with antimony. So what do we get?
KR,
So krypton,
4D10, 5S squared,
so
5P3.
5p3. So that looks good. And so yeah, I just wrote it slightly different order. So that looks good as long as everybody has that. Again, write correct total number of electrons. I'm not too picky whether you write 4010 over 5s2 first, just as long as the total is correct. All right, what about sulfur 2 minus? What do we get for that electron configuration?
Will I be correct if I just wrote argon?
So you probably want to go like previously. So like, yeah, even though it is,
3S2 and 3P6.
so yeah, neon, 3s2, 3p6, but kind of good to at least recognize it's argon, but this is kind of preferred just to show, yeah, because you always want to start at like the previous noble gas. And so again, right, we had to add 2 electrons to this, again, bringing us to argon. We could, if we need to compare it right to the neutral, just kind of start with the neutral in your head. Neon, 3s2, 3p4, oops, sorry. And then, of course, 2 minus means we have to add 2 more electrons to that. All right, what about tin, 2 plus? Somebody else want to go for it? Miriam, what are we thinking? 5s2, 4010, perfect. So that looks great as well. And so this is kind of cool because, right, we can kind of see why tin is one of those with multiple oxidation states. So again, right, think about the neutral. So 5s2, 4d10, 5p2. So we can see right where those 2 electrons maybe go first. So there's one common oxidation state of 2 plus, and then the next to go would be the 5s2, right? So that gives us the tin 4 plus oxidation state. So just kind of cool to see where those electrons are being pulled from. All right, that's a good point for a break or so. So be back in roughly 10-ish minutes. So we'll keep doing practice problems. Okay.
Are there any important announcements for
No, just midterm, and then the lab should be there. But actually, don't we give somebody 2 business managers? Oh, okay, never mind. Okay, no, this was June hours after class. All right, let's keep going. So I had a request online to do one of the transition metals for the electron configuration. So let's try that. So let's just try tantalum there and practice that. Do we have an answer? I'll give people a few more minutes. Or all right, so what do we get for tantalum here? So what noble gas can we start with? So xenon, and then where do we go from there? What does your periodic table say? Should be all labeled, so xenon, and then what's next? So 6s2, good, and then, so then it doesn't matter kind of which one you write next, but we need to get the total number correct. So what do we need in there? What are we thinking? What did we write? So 4F, and then it's 14 though, because you only have 14 in the F. And then go back, so 6S2, 4F14, and then what do we need to finish up on? So what's the big marker? D. So 5D. And then again, if this is 14, we can look at this periodic table. I see it in the chat now, right? So now we're at 5D, 1, 2, 3 there. And so just add up everything if you're confused or not sure, right? So we have 54 with xenon, then 2 for the 6S, then 14 for that 4F14 plus 3, so 73, and you just want to make sure that that number matches right with our atomic number, again assuming it's neutral. So okay, 73, so it's neutral, so I should have 73 electrons. Good. So 5D, 3 there. All right, so let's try a similar but different question. And so now we can have, right, probably made up elements. So I'll say a new element has an atomic number of 135, a mass number of 288. So can you give me the protons, electrons, and neutrons of an ion with a 4+ charge? So again, take a few minutes for that one. All right, chat has answers. Let's see what y'all got and compare. So what do we get for the number of protons? 135, so chat agrees, right? That has to be our atomic number. All right, so then what do we get? Do we want to tackle neutrons or electrons next? Either way. What do we get? So 153 for neutrons, and again, chat agrees with you. And so that one, right, we just took our mass, and that's protons plus neutrons, so you have to subtract your protons to get your mass number. And then electrons, right, we have a +4 charge, so we can compare it to our protons. So how many electrons do we end up with? So 131 electrons, and chat also agrees with that. Did we all get that in here? Do we have questions? I see some yeses. And again, right, electrons, different ways to think about it. So if it's +4, right, electrons are negative, so you have to be losing electrons. You can always set up your algebra too. So if you have a +4 charge, that's equal to protons plus our negative electrons. So I always put little negative signs, so we're adding a negative. Let's try some other problems. So then you have like a naming section. And so this is kind of how it's worded. So it says, give the chemical formula and name of the compound formed from the following pairs. And so again, this is how it's phrased on the test. So chromium 3 and phosphorus. So again, your goal is to write the formula and the proper name. And then ammonium. So what happens when you have ammonium and sulfur? So again, name it properly, write the formula. And then we'll do silver and phosphate. And tungsten 3 and oxygen. And then we'll do one covalent one. So again, this is how it will be worded. So you have phosphorus and sulfur. And again, for covalent, so we have to tell you, so 2 atoms of phosphorus, 3 of sulfur. So what would that make? Write the formula and name it. All right, so try those 5 problems out. Tungsten, tungsten 3, and oxygen. All right, let's hear what we got for these. So what do we get for chromium 3 and phosphorus? So what's the formula? So what ratio are they in? What oxidation state is phosphorus usually in? Meta, what did you get for the formula? Lexiana, did you get a answer for this one? So what's the oxidation state of phosphorus normally? Get your periodic table. What do we see on there? What did you say, -3? Yeah, and so in this case, right, we want it to be -3 though, because it's, it's paired with the metal, so that's probably what's going to be happening. It's not a covalent compound. But then look at the ratio, right, because it's chromium 3 plus, phosphorus 3 minus, so they're already balanced in this 1-to-1 ratio. So our formula is just CRP, so chromium. And then how do we name this properly? So chromium 3 phosphide. Chromium 3 phosphide. So again, don't forget your group 5, right? Nitride, phosphide, arsenide. Those can come up, and they're just, again, in their 3- oxidation state, so don't let them trick you or intimidate you. All right, what about ammonium and sulfur? Either give me the name or the formula. Or you could give me the ratio of how many ammoniums to sulfur. So what's sulfur's oxidation state to? So yeah, -2 though, so make sure. So -2, and then what's ammonium? What's the formula? What's the charge? So NH4 plus, and so now we could maybe do a little swap trick or just see, right, well, we have 1 plus versus 2 minus. So I'm going to need 2 equivalents of ammonium to balance out our sulfur there. And again, I'll draw out our scratch work for the swap trick. So use the swap trick. So 2, 1, so there's our formula there. And then how do we name it properly? So ammonium sulfide. So again, just change that ending to "ide," and we're talking about just one single element. All right, that looks good. Questions on these two so far? All right, so now let's look at silver and phosphate. So you have to remind yourself, what oxidation state is silver always in? And then what's phosphate? So thinking of those two things. So what's silver's common charge? So +1, and then what's the formula for phosphate off of your polyatomic? So PO4, do you remember the charge that it has? So 3 minus, so yeah, just have your chart handy for your exam. And so this is a good one for the swap trick, right? So I'm going to bring my 3 over to silver. So Ag3, PO4 then. And then how do we name it? So silver, and then, yeah, just phosphate. Oops, as I misspelled silver. Silver phosphate. All right, so now look at the next one. So we have tungsten 3 and oxygen. So right, you should be asking yourself, what's the oxidation state of oxygen, and then swapping them. So you can give me the formula or give me oxygen's oxidation state. So -2 for oxygen, and so again, right, use your swap trick. So we have 3+ for tungsten, oxygen's 2-, so swap them to get our formula. So W2O3, and then someone can give me the proper name. So tungsten, and then did you say 3? So, yeah, so tungsten 3 oxide. So just make sure you name the oxidation state. All right, and then our last one, so this is kind of like a freebie, but it kind of has to be for covalent, but we just have to remember how to name it properly. So again, they told us that it's 2 atoms of phosphorus, 3 of sulfur. So what's our formula? So don't overthink it, right? So P2S3, perfect. And then of course the trick is the covalent naming and this one. So what's the proper name? So diphosphorus trisulfide. Excellent. So again, you'll have a portion on your exam that looks pretty similar to this. All right, so let's do another type of problem. And so I don't think we've talked about this explicitly, so we'll go over it. And so we've kind of talked about it in another sense. And so you remember, right, for our average atomic mass, you're given some sort of formula, right, that it's the sum of your percent abundance, right, of isotope 1 times that isotope, right, so times mass 1 or mass n, isotope n. Okay, so we know that, but we haven't seen this type of formula or this type of problem. And so now let's practice this. So gallium has 2 isotopes, and our average atomic mass is 69.723 AMU. And so given that gallium-69 is 68.9255 AMU, and gallium-71 is 70.9247 AMU, what's the percent abundance of each? So just try to think about it initially. So I'll give you guys a few moments to kind of stew on it. How might you approach it? Kind of thinking about what we were doing, right? Multiplying our percent abundance times each mass. And so just kind of think about what you've been given, and then we'll go over how to approach it. So let's talk about it. I think everybody looks a little stumped on how to approach it. And so let's think about what this is saying. And so this has to be a special case, right? So we can't just obviously add up, anything or solve it for anything. So the key is that it only has two isotopes. So that's going to be the key on your exam. Okay. And so let's think about what it's telling us to set up, right? So we're basically trying to figure out the percent abundance of each, so X and Y, let's just say. And then by definition, well, there's only two isotopes, X plus Y have to equal 100% or 1, because, right, again, we want to convert it to the decimal format for the abundance. So X plus Y equals 1. And well, now we have two variables, but we could set y equal to 1 minus x. And so now maybe you can see where this is going. And so now we can write our setup. So, okay, if our average, sorry, I got to do some scrolling. So 69.723 is equal to, and then, right, pick which one's x, which one's y. It doesn't really matter. But now I'm going to rewrite y as 1 minus x. So we'll plug that in. And so now we can set up our algebra. So is equal to x, whatever that percent abundance, times our mass, so 68.9255. Plus 1 minus x, so 70.9247. So from here, it's just algebra. So this is, like I said, the important setup part. So you want to be able to get to here and kind of understand how to do that. And so now just take a minute. I'm going to let you try to finish up the algebra before I go over it. And then you can double check my algebra. So just solve, right? You mainly have to distribute. Solve for x. So do we get that x is 0.6 then, after doing the algebra? So again, I just kind of wrote it out now. So just distribute everything, and then you have to subtract, right? So moving 70 over gives us negative 1.992, or excuse me, negative 1.2017. Move the x's to the other side. So again, subtract, right? So now we have negative x, and then x 60 there. And then again, just remember, right, these decimals, when you convert it to percentage, it's by 100. So 60% for x, and then obviously that leaves y at 40%. All right, last type of question that we'll have is drawing some sort of Lewis dot structure. And so let's try a practice. So let's do our nitrate anion, so NO3 minus. And so with that, tell me, is it polar or non-polar as well after you get the structure? And then what's its geometry? So take a few minutes to sketch out nitrate. And again, there could be resonance structures, so make sure to include all relevant resonance structures. So let's go over some of the permutations that you should have drawn on your paper. And so you can, of course, start with the simplest kind of structure, putting a line to each one. And again, right, keep track of your electrons because that's important. So nitrogen brings 5. Each oxygen brings 6. And then negative charge, so plus 1 electron. So now we're at 24 electrons in our system. And so like I said, this was a perfectly good starting point. And now I'm just filling in my electrons, right? So I have 24 electrons. Now let's talk about what other things we need. So we need formal charges. So this has a 2+ formal charge. Again, I can do the scratch work really quickly. So 5 valence electrons minus 1, 2, 3. And then, of course, no lone pairs on there. So that leaves us with a 2+ charge. And then all these oxygens. So, right, 6 minus 1, 2, 3, 4, 5, 6 minus 1. So all of them have a -1 charge. And so then with that, we might think, okay, well, let's maybe draw a bond here and try to eliminate some of these formal charges. And you can, of course, right, get different permutations. So you probably want to end up with 2 double bonds. Although arguably, right, that's not great for the octet rule. So this one you can have, right, a few permutations of valid answers. And so this is fine. We just still have, right, a positive formal charge on the nitrogen, 2 negative ones on our oxygen. So that's fine. And right, so I would probably stick to these since they have 8 valence electrons. So again, if you had written this out, I don't think that I would mark it wrong. But let's just talk about the structure. Right, again, now we've at least minimized our formal charges, except nitrogen does not typically go hypervalent. Remember, it's just too small. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 electrons, right? Nitrogen, not typically hypervalent. And so this would be like a very nice answer if you express that. Otherwise, I'd just be happy that you had the correct total number of electrons, and again, right, formal charges. And the other thing to note, well, okay, we can draw, right, all these different permutations, move the double bond around. And then in all these cases though, so right, again, you're averaging out the structure. We could go back to this one and determine polarity, right? So kind of the average. What do we get for polarity then? So nonpolar, right, it averages out in all directions. So nonpolar, all evenly distributed, good. And then what's its geometry? Again, look at how many things it has attached to it, no lone pairs. So what geometry does that make it? So look at your compound chem sheet if you need some inspiration, right? So you said trigonal planar, correct? Excellent, so trigonal planar. So that looks good there for an answer. So again, key points, right, is that you have the correct number of electrons. That's the most important, right, your total electrons. And then it's always good, like I said, to identify formal charges if they're there. And then you're also thinking about, again, fulfilling the octet rule. So it would probably be best to note, again, just for a complete answer, that we only have 6 electrons here. So, right, maybe this is not super ideal in terms of the structure. But as long as you're just like pointing those things out to me, right, I know what you're thinking, I know where you're coming from, then I can see, you know, kind of how your thought process is. Because it's not just about getting, right, the right answer, it's about how you approach it, annotating it, again, right, having these total number of electrons correct, all those sorts of things. All right, I think that pretty much covers it. Oh, the only things that we didn't review was just solving for molecular weights of compounds. So I think you're given some formula or maybe asked to name it and then solve for the molecular weight. So again, just adding everything up. And then there might be like a percent mixture question as well. You know, it could be either like the sand has X number of grams, right? The salt is blah. How much is each percentage of the total? Or it might give you the total. So that type of question. But yeah, otherwise, we went over everything that's on the exam. At least, like I said, for the in-person exam, the online exam is a little different, but. All right, any other questions, comments? All right, so I'll post this review. I need to post the sharing link still. So I'll do that now, and then of course, if you have questions, you can hang around after class or email me if anything comes up. And then it is open notes, so right, just think about what resources you need to have. I would maybe sticky note your textbook, relevant pages. You know, you don't want to spend too much time trying to learn on the exam. You're just trying to like, what do I quickly need to reference, right? Have that handy, have whatever relevant examples queued up. You know, have the midterm review ready to go so you can reference it. So just think strategically so that you have your resources. All right, good luck. I'll see you Wednesday for lab, and then otherwise for lecture.
So the midterm will be on Monday?
No, Wednesday.
Wednesday.
So, yeah, this Wednesday.
Will it be during recitation?
It'll be during the whole class period. So yeah, we won't have class, well, we won't do lecture on Wednesday. We'll just take the exam as soon as you get in. at 1, and then, yeah, I flow into recitation. If you need a little extra time, it's there. I can't remember, I don't think we have accommodations.
I think I might be missing one of the notes that you handed out.
Like,
One of the sheets that you gave out for us, cheat sheets for.
like the compound CHEM one, or which one?
It was, I think it's the one that like